Alright, here we go. Introduction to Chemical Kinetics. In chapters 5 and 19, we studied the variables of enthalpy, entropy, and Gibbs free energy. Enthalpy was defined as the sum of the internal energy, that was made up of your potential energy and your kinetic energy, as well as the work that gets done. And the work that we talked about was our PV work, our pressure and our volume work. Okay. We essentially used it as a way of measuring the heat transfer during a chemical reaction. Because if you remember, we talked about how work doesn't really get done unless a volume changes, and that only happens when gas is produced. Okay? So for the most part, 99.9% of the time, the enthalpy that we're talking about has to do most directly with the energy changes or the heat transfers that we indicate, okay, that we measure. Okay. Often, this was a useful predictor when deciding whether a reaction would occur at all. Generally, we found an exothermic reaction, which would be one having a negative enthalpy, occurs spontaneously. To be absolutely certain, however, we needed to pair enthalpy with entropy and the temperature to generate a third variable called Gibbs free energy. Because the temperature of a system and the changes that occur, the energy changes that occur during a reaction, and the tendency towards greater entropy all affect the spontaneity of a reaction, we needed to combine them all in order to be certain of our conclusions. Our new chapter builds on this particular bit of information. Before, in chapters 5 and 19, we were only able to assess if a reaction would occur, if it's going to occur spontaneously at least. Kinetics provides us with the skills necessary to assess the rate at which a reaction will occur. So before we talked about if, now we're talking about rate. We're going to study rate, how to determine it experimentally, and what we can do to affect the rate of reactions. Understanding kinetics is what allows scientists to control how fast reactions occur. This can be pretty useful information. For example, suppose a pharmacist is developing a new drug, such as perhaps a new form of aspirin, that will react quickly in the body so that pain relief is rendered as soon as possible. But he or she wants to pair it with another form that will react slowly so that the effects will last a longer time. The pharmacist uses the principles of chemical kinetics to discover the mechanism or the process by which a reactant such as aspirin, is absorbed, broken down, and utilized by the body. Understanding the steps of a reaction is the key to controlling it. So, to begin, what does it even mean to have a reaction rate? When discussing the rate or the speed of a car, we generally compare the distance traveled in a given amount of time. Usually this is done in miles per hour, kilometers per hour, kilometers per second, are some examples. In chemistry, the thing that changes over a given amount of time is going to be the concentration. Generally, we discuss the change in concentration of the reactants. And so oftentimes what we wind up with is a negative value. This is done because as a reaction proceeds, the concentration of reactants will decrease. We can also discuss the rate of a reaction from the perspective of the products. The example that's given in your book, let's go to that real quick. The example that's given in your book has to do with the decomposition of dinitrogen pentoxide. And that breaks down into nitrogen dioxide and oxygen. The rate can be given from the perspective of the diminishing reactant in this way. So we could have diminishing N2O5 over time. It can be given as the increasing amount of NO2 over change in time. And it can also be given from the perspective of the increasing concentration of oxygen over time. And again, we have that negative sign in front of the reactant. When comparing the rate of a reaction from these different perspectives, it's also important to use the coefficients from the balanced chemical equation. going to look like this. And 2/1. Okay? It's sort of like taking the inverse of these coefficients. If we move from looking at the equation to looking at the graph of this, we have, as you can kind of see here, the concentration on the y-axis and time on the x. Okay? We have concentration over time. It's important to notice from this graph that as you progress through time, the rate of the reaction, or the slope of the line, decreases. Okay? This occurs because as you use up your reactant, the rate of the reaction is going to effectively get slower and slower. Okay? Less reactant equals a slower reaction. Okay? And you're using it up as time progresses. Another aspect that is important is the fact that there are two types of rates that can be determined from this graph. The first type is the average rate. This is what we've been discussing. The change in concentration over the change in time will yield an average rate over that given amount of time. However, we also just talked about the fact that rate changes as the reaction progresses. Therefore, sometimes it is useful to calculate something called an instantaneous rate. This is the exact rate that a reaction is progressing at one particular point in time. This is pretty analogous to looking at a speedometer while driving a car. At any given time while driving, you can tell the speed at which you're going, but this does not necessarily reflect the average speed you travel over an entire journey. In chemistry, instead of a speedometer, we have our graph. To calculate an instantaneous rate from the graph, simply sketch a point on the line and calculate the slope of its tangent. Okay? Such as right here, we would then draw a tangent line, and the rate at this point would be the slope of that tangent line. Since the slope of the line in general on the graph is the rate, the average slope over time is the average rate, and the tangent's slope at a given point is the instantaneous rate. Okay. This time, pause the video and just practice exercises 15.1 and 15.2 on page 675. All right, I said already that the reaction rate slows as a reaction progresses because of the diminishing availability of a reactant. Temperature and the presence of a catalyst are also ways of affecting the rate of a reaction. Remember how many things relate to the geometry of chemical compounds and even more directly to their potential for intermolecular bonding? For example, a polar compound will be attracted to other polar compounds via dipole-dipole bonding. A nonpolar compound will be attracted to other nonpolar compounds via London dispersion forces primarily. Actually, that would be it. If you increase the temperature of a system, you increase the kinetic energy, and therefore you disrupt the ability of the intermolecular forces to bind molecules together. As the molecules separate from each other, they become more accessible to other reactants. The increased energy also increases the rate and speed of the collisions, which increases the rate as well. Increased energy also allows reactants to overcome the activation energy, or the minimum energy required to react. Okay? That's depicted on this graph as this sort of rise of energy that's required before a reaction can actually progress. Okay? This is going to be something we talk about more towards the end of this chapter, but it's not a bad thing to keep in the back of your minds. Okay? The other major way of increasing the rate of a reaction is by introducing a catalyst. A catalyst is a substance that doesn't affect the products that result from the combination of two reactants, but it does provide them with a more energy-efficient pathway to react, and thus allows them to react quicker. You can think of a catalyst as a substance which allows reactants to take a shortcut to completion. Lastly, if a reactant is a solid, the reaction rate can be increased by increasing surface area. The greater the surface area, the more reactant that is showing that would be available to react, and therefore, of course, the faster the reaction. Okay? So in terms of our ways of increasing a reaction rate, we've talked about temperature, a catalyst, the concentration of reactant. If you keep adding in reactant, you'll keep the reaction going nice and fast, relatively. And the energy for the activation energy, as well as if it's a solid, the surface area. Okay. All right, to finish up, turn to page 712 and complete questions 2, 4, and 6. I'm going to collect those on Monday with the work that you did from page 675. All right, thank you.